That's column 3. That's the column 0, minus 1, and 4. This guy. So, again, what's my problem? What this equation is asking me to do is to combine these 3 vectors with the right combination to produce this one. Well, you can see what the right combination is, because in this special problem, especially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work? I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1. That's the combination. None of that, one of those is obviously the right one. So this column 3 is actually the same as B in this particular problem. I made it work that way just so we would get an answer, 0, 0, 1. So somehow that's the point where those 3 planes met, and I couldn't see it before. Of course, I won't always be able to see it from the column picture either. It's the next lecture, actually, which is about elimination, which is the systematic way that everybody, every bit of software, too, production, large-scale software would solve the equations. So the lecture that's coming up, if I was to add that to the syllabus, will be about how to find x, y, z in all cases. Can I just think again, though, about the big picture? By the big picture, I mean, let's keep this same matrix on the left, but imagine that we have a different right-hand side. Oh, let me take a different right-hand side. So I'll change that right-hand side to something that actually is also pretty special. Let me change it to, suppose if I add those first 2 columns, that would give me a 1 and a 1 and a minus 3. There's a very special right-hand side. I just cooked it up by adding this one to this one. Now, what's the solution with this new right-hand side? The solution with this new right-hand side is clear. Now I took one of these, and none of those. So actually it just changed around to this when I took this new right-hand side. Okay. So in the row picture, I have 3 different planes, three new planes meeting now at this point. In the column picture, I have the same 3 columns, but now I'm combining them to produce this guy. And it turned out that column 1 plus column 2, which would be somewhere there is the right column. One of this and one of this would give me the new B. Okay, so that's like we squeezed in an extra example. But now think about all B's, all right-hand sides. Can I solve these equations for every right-hand side? Can I ask that question? So that's the algebra question. Can I solve AX equal B for every B? Let me write that down. Can I solve AX equal B for every right-hand side B? I mean, is there a solution? And then, if there is, elimination will give me a way to find it. I really wanted to ask, is there a solution for every right-hand side? So now, can I put that in different words? In this linear combination words? So in linear combination words, do the linear combinations of the columns fill three-dimensional space. Every B means all the B's in three-dimensional space. So do you see that I'm just asking the same question in different words? Solving AX, oh, that's very important. A times X, when I multiply a matrix by a vector, I get a combination of the columns. I'll write that down in a moment. So that, you see, but in my column picture, that's really what I'm doing. I'm taking linear combinations of these three columns, and I'm trying to find B. And actually, the answer for this matrix will be yes. For this matrix, for this matrix A, for these columns, the answer is yes. This matrix is this matrix that I chose for an example is a good matrix, a non-singular matrix, an invertible matrix. So those will be the matrices that we like best. There could be other, and we will see other matrices where the answer becomes no. Oh, actually, you can see when it would become no. What could go wrong? How could it go wrong that out of three columns and all their combinations, when would I not be able to produce some B off here? When could it go wrong? Do you see that the combinations, let me say when it goes wrong. If these three columns all lie in the same plane, then their combinations will lie in that same plane. So then we're in trouble. If the three columns of my matrix, if those three vectors happen to lie in the same plane, for example, if column 3 is just the sum of column 1 and column 2, I would be in trouble. That would be a matrix A where the answer would be no. Because the combinations, if column 3 is in the same plane as column 1 and 2, I don't get anything new from that. All the combinations are in the plane, and the only right-hand sides B that I could get would be the ones in that plane.